Okay, so exam 2 next week, same as exam 1. Real nice. Any questions about exam? If you have a schedule conflict or something, you think you might need a different time frame, let me know. Shoot me an email. I'd be happy to accommodate you. So those of you who know me know I'm happy to accommodate. So keep me posted on your situation. I think that's all I want to say about that. And so I will now open the floor to, do you have a specific question from homework, Mr. Paul?
I do. I have several.
Yeah, start. Where do you want to start? Questions are good. That's how we learn.
All right. The first one is a minor question.
Yes.
For 7F.
7F. Okay,
Yes.
what's the minor question?
So the natural log of 0 is undefined, correct?
Well, that's the whole point of this problem, right?
Right. So I know that it diverges, right?
It does diverge, correct. And the reason is, well, let's just work through it, because this is an important, look, well, let's just work through it. And then maybe you're discovering some cool stuff, and that's always good, Paul. We like when people discover things. So let's look at homework 5 help here. We'll call this homework number 5 help. So if we look at, this is 7F, right? And what we want to compute is this integral. So here's the correct way to write things down. So what you're noticing is this. So let's say, what is this? So here's an incorrect argument. And it's just a subtlety, but if we want to write things that are making sense, and we want to understand things, here's what we should do. So here's the incorrect argument. The incorrect argument is to just go ahead and blindly use the fundamental theorem of calculus. And the reason that this is incorrect argument is because 1 over x is not defined at 0. So you cannot make this argument. This is gibberish, even though this argument leads to the correct answer. So the reasoning is flawed. And if you apply this reasoning to other problems, you might not get the correct answer. You might get a nonsense answer.
So you could assume from 0 being undefined that the value of 0 would be an asymptote, right? So then would you have to separate it into 2 integrals, like approaching it?
You don't even have to do that. So the correct way to do it is like this. So here's the correct argument. So let's first off, let's make sure everybody understands why what we did before is incorrect. So the above is incorrect. And it has nothing to do with the fact of the last line, other than the above is incorrect because we can't apply the FTC because the log of 0 is undefined. So you're using a big theorem. You're using the fundamental theorem of calculus illegally. Now, it just so happens in this particular problem, by coincidence, you get the right answer. Because if you look at the previous line, you're going to say, Paul, you're going to say, well, log of 0 is undefined. So I'm going to reason that this whole thing is nonsense and it's undefined. Because you get 0 minus, if you want, you can argue infinity. But that's not correct reasoning. We can't treat infinity as if it's a number. Infinity is a concept. It's the symbol, this like sidewards 8 that we use for infinity. It's not a number, so we can't do algebra with it or arithmetic with it. So here's the correct argument, the correct way that we should do this problem. Here's the correct one. So since 1 over x is undefined, at 0, the integral is improper. So this means, by definition, Paul, by definition, the correct way to do this is you don't use two integrals. What you do is you use a limit. So we are going to take the limit as delta approaches 0 from the right of this integral where I go from delta to 1. Because now this makes sense. And so the correct thing is to write this as the limit. Now you can now apply the fundamental theorem of calculus, because this is the log of 1 minus the log of delta by the FTC. So now I'm legally allowed to use the FTC because delta is a number that is not 0. I mean, it can't be 0. If I'm telling you delta is a variable that approaches 0, then it can't be 0 by definition. And so now this reasoning makes sense. And then what we do know is we know the log, we know this guy right here is equal to 0, the log of 1. So then the next piece of reasoning is that this limit now the problem is we know the limit is equal to minus infinity, because the limit as the log of the variable goes to 0, we know that it is negative infinity. So you get minus infinity. So what is the conclusion? The conclusion is the integral diverges. It doesn't converge. So if you look at the instructions of the problem, it says determine the value of. It shouldn't say or, it should say of. I have to fix that. Determine the value of the following improper integrals if they converge. Well, this guy doesn't converge because the limit's infinity. The limit doesn't exist. Does that make sense?
Yep.
So it might seem like I'm nitpicking, but I'm not. So you have to be very careful. These improper integrals are very delicate, and if you use the tools wrong, if you incorrectly try to apply theorems, you can get incorrect answers. So you have to be very careful about that. And coincidentally, I mentioned this on Tuesday. These improper integrals are typically something they give students a lot of. They give you guys a lot of problems, and they gave me problems. So, for example, a lot of students take calculus in high school, and the calculus sequence in high school, they usually don't do these improper integrals, and they usually don't do those trig substitution ones. And I think the reason is they're just so difficult for most students to learn. So often you guys just want to throw that infinity symbol around, but you have to be very careful. You can't just write things because they look like they work. There's a correct way and an incorrect way to write this. So I hope that makes sense, and I hope you guys will take some time to study this example. That would be my dream as an instructor.
Awesome. I just wasn't sure exactly how. I knew the ends, but not exactly the argument to use.
No, that's right, and that's the reason I put this problem on there. And really, look, any one of you could go to the Google machine and type this in, and they're going to say the integral diverges, and that's fine. But the understanding is the more important thing. Look, if you're looking at my opinion on what I sort of think is important, my goal for students is to want. And I know this is hard and it's a big ask, but my ask of you is to try to understand what's happening. And these are hard things, and it's so easy for us, especially now that technology's there. It's so easy for us just to go get the answers. But when we do that and we don't fill in the details and make sure we understand them, we're missing the bigger picture. You're missing the logical development, the training of the brain to think in a reasonable manner. So often we think of math as just computation, and it's really not. Math often gives us swift tools for computing. But the goal really of mathematics is to have understanding and reasoning and recognizing patterns and it's deeper than just computing something. There's a famous saying, I forget which mathematician said it, but they said the cost of doing science is computing. And the point of that is understanding how things work is more important than being able to compute. And the unfortunate thing is oftentimes the computation takes forever. I mean, think about what the integral does. If you go way back to the definition of the integral, it's quite a fascinating thing. It literally says we are going to take a process that is infinitely long, and we are going to turn it into an arithmetic operation. So if you go dig deep in what the integral means and its definition of this limit of Riemann sums, it's really taking a process that theoretically is never ending, and it's turning it into arithmetic when you apply the fundamental theorem of calculus. So it's quite fascinating how that works. The thing is, it took humans thousands of years to develop the appropriate language and understanding to be able to make sense of that. So yeah, you don't want to get discouraged with this stuff. You want to understand that it's hard and it's confusing, and just when you feel like you made sense of it, 20 minutes later you don't. You're like, what? So that's part of the fun, at least to me. Then again, you're going to say, why do I have to like it just because you like it, O'Grady? To which I say, touche. All right. Any other questions on the problem 7 while we're at it? Or, I mean, I'd be happy to answer them. If Paul, if you want to be the speaker of the house, feel free to talk. But I'm happy to do any of them. That's what we like to do. Someone's chapping. But there you go, exactly. And now, in many ways, some people will describe calculus as like the taming of infinity, because that's what it does. It's really, if you think about what we're doing with all these limits, is you're really playing with a war. And what's happening is one thing gets large, something else gets small. And who's winning? The things that are getting small, or is it the things that are getting big? So in this case, the things that are getting big win because the integral diverges. But if you look at an example like 7a, like we did in class on Tuesday, there the small guys win. It goes to a number. Okay, any other problems on this homework? Number 8 we'll save for last because that's the most difficult one, but I'm happy to do any of the other ones.
Could you just, I wasn't exactly sure how to start 5 and 6.
Okay, so right. So this it's interesting because I could have worded these problems in lots of different ways. And really, 6 is very much connected to F. And I don't know if you've paid attention in your book, but if you guys have the newest version of the book, it's chapter 7. So if I can digress for a minute, there are 2 sort of standard ways of teaching calculus. If you look at our textbook, it says early transcendentals, and most students in calculus have no idea what that means. And then there's another version of this book, which is blue, that says calculus, and it just doesn't say early transcendentals. And the only difference in this book and that book is in which order are things presented. So the fact of the matter is, if you remember back in Calc 1, we just tell you the derivative of e to the x is e to the x, right? We don't really show you why. And that's because it's difficult. But the issue is from a logical standpoint, some math people don't like teaching that until they can tell you why. So if you look at chapter 7 in your book, chapter 7 develops the logarithm and the exponential function from what we say first principles. It develops it by defining the log as an integral. And I don't want to go into all that because this is, I mean, I'd be happy to outside of class if you're curious. But I don't, being that we introduced the exponential function and the logarithm way back in Calc 1, we're just going to assume they're defined in the way that we defined them. But what we can say is there's 2 ways to develop, and this is, maybe I'll write this down. even though this technically doesn't have anything to do with the problem. So cool fact. So there's two ways to define the function y equals the natural log of x. Method one, as the inverse of y equals e to the x. They're inverse functions. Method two is you can define it actually as an integral. This is the logically sound way of doing it. This is how it's defined in advanced books. And the reason for that is because it's just the rigorous development is what's important to people. So either way, it's the same function. So let's be clear. And again, I don't say this to want to confuse you. I say this because, well, if you read the book, you'll learn this. So either way, is acceptable. And so that's what the textbook means. If you do the function, if you use the book called Early Transcendentals, they use this method. And if you use a regular calculus book, they define it using this definition. Either way, it's the same function. All right. Okay, now, using method one, the fundamental theorem of calculus gives so by method one, FTC gives it gives the integral of, say, 0 to, let's say, b, just for lack of a better word, of 1 over x, using the fundamental, not 0, 1, excuse me. So let me be try to write this a little more clear. So by the fundamental theorem of calculus, you get this to be the log of b minus the log of 1, which of course just simplifies to the log of b, because the log of 1 is 0. The natural one. Log of 1 is 0. So using the fundamental theorem of calculus, you can write any logarithm as an integral. Is that clear? So for example, the log of 5 is nothing more than the integral from 1 to 5 of 1 over x dx. Man, I am sloppy today. So this is one way to obtain what I'm saying. So that's what I meant by problem 6. To write log like this, and then you can approximate the log of 5 by determining the area under the curve or calculating that integral. So this is a good sort of problem. Problem 5 and 6 are, I mentioned them at the end of class on Tuesday. They really start to, and this is why they're so confusing for amateurs like yourselves, is that you still, guys, most of us in a calculus class, calculus 2 class, even undergraduate math and engineering majors, we have such a hard time of distinguishing between exact and approximated. This symbol right here, ln of 5, that is a symbol. That represents a number that goes on forever and ever and ever. Just like pi is a symbol humans created that represents a number, 3.14, blah, 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 blah. Just like E is a symbol that we use to represent what we call an irrational number, a number whose decimal goes on forever and ever and ever. Log of 5 is an irrational number. If you go to a calculator and hit 5 and then log, it's going to tell you what it is. If you go And that's fine. But what we want you to do in this problem is we want you to see how you can use calculus to approximate that number. Because here's a very cool thing. If you interpret this geometrically, then the log of 5 is precisely the area under the curve 1 over x between 1 and 5. And so if we compute that integral numerically, then what that's doing is that's giving us an approximation of the area under the curve, and hence it's approximating log 5. So before I go any further, does anybody have a question about what I'm saying? And we're going to actually do this problem for you.
That helps a lot. I just didn't put it together that...
Well, you wouldn't. And look, this is, I was about to be a smartass, but that's the genius of me, and I'm saying that jokingly. But one of the things I know is that if I word the problem this way, I'm going to get that question. So these problems are put that way so that it can motivate us to discuss this. Now, if I just wrote down, use Simpson's rule on this integral, there's no learning experience there. You're just repeating some little program, some algorithm, right? But if I phrase the problem this way, then there's a learning moment that happens if you want it. And the learning moment that happens is that number, the log of 5, can be geometrically thought of as the area under a curve. So if we're being even more, if I want to be very specific with the geometric interpretation, if I draw my XY axis and then let's draw this curve. So what's the curve, of, well, let's be specific. So if we talk about, so this is 1 and 2 and 3 and 4 and 5, right? And so we can talk about, I'm going to change the scale here. Let's put this to be, we'll put this as 1. The reason I'm changing the scale is so you can see, this curve goes through the point 1, 1. Then it goes through the point 2, 1/2. And it goes through the point 3, 1/3, etc. So what's this curve look like? Well, even though and you could go to Desmos and graph it too, but it's going to look something like this. Oh, I'm off. My hand moved. So let me be a little more careful. We know it has this asymptote. So it's looking like this. So what we're saying is this region right here. So the blue shaded region has area equal to the log of 5, but in terms of the integral, the blue shaded region is this integral. So we're connecting geometry, and this is a pretty ingenious idea. This has given you some insight on how people may have computed logarithms 200 years ago. I mean, students in your generation, and even mine, we fail to forget that the calculator world is very recent. If you were a physics student or a math student or an engineering student in the 1950s, for example, or the 1920s, or the 1800s, you would have had to purchase separate books with your textbooks. And in these books, all they were tables of values, because a bunch of other nerds had to sit around all day and calculate logarithms and calculate the values of sine and cosine, because you didn't have calculators. You had to look them up in a book. Square roots, for example, had to be looked up. And so at one point, long before calculators, humans had to figure out, how do we determine these numbers? Now, there's lots of ways to do it. This is one of the ways to do it. So the reasoning you might have is as follows. You might have this reasoning. You might say, okay, cool. The log of 5 is this integral. So we know that's the exact value of the integral. And so if we want to know an approximation of the log of 5, what we can do is we can apply a rule. So in this particular problem, I asked you to do the trapezoid rule. So what does that mean? Well, this means that this is approximately what? Well, it's approximately delta x over 2. And then we have the following. I asked you to do 8. So it's going to be f evaluated x sub 0 plus 2 times f evaluated at x sub 1 plus 2 times f evaluated at x sub 2. And then that goes on, that pattern goes, and then it's 2 times f evaluated at x sub 7, and then the last one is f evaluated at x sub 8. Okay, so that is what we have to compute. Now, you could do this by hand, plugging it into a hand calculator, but I'm going to show you a shortcut way of doing it. There's lots of places you can do this. Desmos is a good place to do it because you can kill every bird with one stone. So before we do this, though, we need to know what this delta x is, right? And we need to know what these x sub 0, x sub 1, all the way up to x sub 8 are. So before we write down what those are, does anybody have a question? Comments, concerns? Okay, so how are we going to determine these values? Well, when you're integrating from 0 to 1, it's pretty simple to get these x naughts and x 1s and x 2s. But when you're integrating from on a different interval, it's a little trickier, so you have to be careful. So the first thing we need to do is we'll come down here and we'll set aside get a different color so we're not all rushing. How about we'll use this purple. So what's delta x? Well, our delta x is 5 minus 1 over 8, which of course is 1/2. That's our delta x, because the integral is from between 1 and 5, so we take our b minus a over the number of trapezoids we're going to use, which is 8. So 5 minus 1 is 4. 4 over 8 is 1/2. So that's good. Now, what are our x's? Well, our x sub 0 we know is 1. And then what's our x sub 1? Well, it's 1 plus delta x, which is 1/2. Now, of course, you'll recognize right away that 1 plus 1/2 is 3/2. Oops, I shouldn't have read it with I should have written it or wrote it. So 1 plus 1/2 is 3/2. And then x sub 2 is 1 plus 2 over 2, which becomes, of course, 3. Or excuse me, becomes 2. Go on. So right away, you start to see the pattern. So this is, we get 3/2. And then 2, another way of writing 2 is what? Well, another way of writing this is 4 over 2. So once you do that, you get the pattern. So x sub 3 is 4 over 2. So you get 3 over 2. Then you get, I just had a typo. So I'm saying another way to write x sub 2 is 2 over 2 is, so let me write it this way. 2 over 2, put these all over 2, and you'll see the pattern. So what do you have if you put it over 2? You get 4 over 2. And then x sub 3 is 5 over 2. And then x sub 4 is 6 over 2. So you get the pattern once you do the first few. And then, of course, this goes all the way up. If the pattern's correct, what is x sub 8? Well, the numerator's 2 more, so this should be 10 over 2. But, of course, that is correct because we know that's 5. So we have the pattern down. So perhaps you might have to think about that. This is one way of doing it. It's not the only way, but this is the way it was easiest for me to learn it when I was sitting in your position. Does anybody have a question about this? It was funny. I was teaching a class once, and we were doing this real hard thing. So I taught this class one summer. It was called Intro to Applied Math, and we're doing this we're studying a pendulum. Maybe some of you've done this in physics. And we're deriving the equation of a pendulum, and then we were talking about how we're going to simulate it on the computer. And the one student literally said, "I'm done. This is too hard," shut their book and walked out of the room. I said, all right. So maybe that's what happened to you guys right now. You're just like, I'm done. I'm out of here.
Well, I thought about what you said about giving up calculus for something like basket weaving. So I tried art, but they said that my work was derivative, so I'm back where we
See, there you
started.
go. That's a good joke, actually. That reminds me of some of the great math jokes I heard as a kid. What do you call a boiling pot of water on a stove? A high pot in use. See, this is what the math nerds do. Good for them.
See, I was going to ask if you could derive square roots by growing carrots in cubes.
That's a good, I actually enjoy that. That's a good one. I never heard of that one before. Someone once bought me a book of math jokes, because people, when you're like a math professor, people just buy you math shit all the time. And some you're like, cool, and others, I swear, I'm sorry. My kid will come down. I heard you. And then sometimes you're like, thanks, but no thanks. But, you know, such is life. Math jokes. All right. So hopefully you guys will convince yourself of what those numbers are. And the reason I was writing them that way is because you hopefully see a pattern. You can clearly see the pattern. If you really want to go to the beginning, what is x sub 0? Well, it's 2 over 2, and then 3 over 2, 4 over 2, blah, 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 blah. Okay, so what I want to show you now is a quick way of doing this using Desmos, so that you don't have to waste your time plugging things into a calculator. And as I said on Tuesday, if you're interested in learning programming, Michelle, I think you sent the email, Michelle. I'd be happy to share and some simple code for doing this, and you can write a couple line of code and you can have the computer integrate real quickly for you. So at least do this trapezoid rule and stuff like that. Okay. Okay. So what I'm going to do is I'm going to go to our friend Desmos. So I have to find him first. Desmos, where did you go? You left us so far from home. All right. So I'm going to go to Desmos. Here it is. Are you guys seeing Desmos? Hopefully. Everybody seeing Desmos? All right, cool. So there we go. All right, so what I'm going to do is, if you notice, I'm going to type in explicitly f of x equals our function, which is 1 divided by x, right? Now, I don't care what the picture looks like right now. I'm only going to be interested in this workspace on the left-hand side. So what do I want to do? I want to add these things up. So let's remember what they are. They were f. Here's what I want to add up. I want to add up f of 1, that's the first guy, plus 2 times f of, who was the next guy? Well, the next guy was, so 1, and then it was 3/2, right? And then it was plus 2 times f of 4/2. And then it's plus 2 times f of 5/2. Whoops. And then it's plus 2 times f of 6/2. Plus 2 times f evaluated at 7/2. So if I write these numbers in this form, I see that there's a pattern. And then that's the last guy, right? Because the next guy, oh no, it's not the last guy. What am I saying? I have 8 of them. 2 times f of 8/2. And then plus 2 times f of 9/2. And now I know that I have the very last guy is f of 10 halves, which is just f of 5. So notice that everybody but the two, everybody but the first and last have a 2 in front of them. So this is great. So now I get the number. I get, when I add these up, I get 6.5, blah, blah, blah. Okay, so now I can really get creative and I can put a parenthesis here. And then I can go all the way to the beginning and I can put a parenthesis. And then out in front, I can put my delta x over 2. Now my delta x was 1/2, so 1/2 over 2 is 1/4. And now I get the answer of 1.6289, blah, blah, blah. So before we skip out of here, does anybody have a question about this?
I have a quick question.
Yes.
So we're using f of x as 1 over x?
Because that's what we're integrating, yes.
Okay. I was wondering, why are we using 1 over x as opposed to ln x?
Well, ln is, no, because we're integrating 1 over x. It turns out that the antiderivative of 1 over x is the natural log, but we're not integrating log. We're integrating 1 over x. So that's another subtlety. That's a good question. We're integrating. If you go back, Paul, what are we integrating? We're integrating, if you look up here, we're integrating this creature right here, 1 over x. So that's
I get it.
Yep. So but that's an easy confusion. That's a common thing to get confused over. So while we're here, what we can do though is we can write the answer. We know what this is. We just calculated it, although I can't do it with an arrow. I got to do it with a pen. And so we get 1.62. Let's round 897. We'll round. Now compare that with what you get on a calculator. For example, if I go to the Google calculator and compute log of 5, I get 1.609. So I'm accurate to 1 decimal point. Does anybody have a question about that? I take your silence as no. So again, why are we super accurate? Not really, but if I used more rectangle, excuse me, if I used more trapezoids, I would increase my accuracy. Here's a cool thing. I'm going to teach you a trick. Maybe you already know this. Let's go to our friend Wolfram Alpha. Wolfram, it's smart. Watch this. If I type in Wolfram, integrate 1 divided by x from 1 to 5 using the trapezoid rule with n equals 8. It knows what I mean. So I just typed in, I literally typed in what the problem was. And now I'm going to be able to check my answer. So it'll take Wolfram a few minutes to interpret what I said, and look what they got, 1.62897. That's the same damn thing we got. And then they even give you the exact result at the bottom, 1.609, which is the log of 5. Isn't this an amazing? Oh my God, and we have a parade of children. What's up? You're taking paper upstairs? Okay. They don't, okay, you get some paper. High five, Ricky. Okay. If you see behind me, this is the kids' playroom, so they're coming down to get their drawing. You guys gonna do math? Please do math. Do your numbers, please.
I'm doing my workbook and Ricky's gonna call.
Do your aeronautical engineering. Okay.
I know what you.
Okay, go do your numbers, Ricky. Okay. Sorry about that. Report me to the authorities for having children screaming and yelling.
It looks like you don't need a calculator. It looks like you got a slide rule behind you.
Yeah. Oh yeah, yeah. I do a big ruler. But that's a ruler. That's how the kids measure their height. Yeah. But that's good. You know what a slide rule is, Paul. We should make you guys use one of them. So look, Wolfram, you could verify your answer with this. By the way, what if I used instead of 8? What if I used like 20? So watch how much more accurate I get by going up to 20. So it takes it a moment to, it gets 1.6, 1, 2. So it's actually not that good. It's getting there slowly. It's not getting there fast. Here's something else. What do you see right now? Do you guys see Desmos or still Wolfram? Probably Wolfram still. So let's make sure, let's see how we can get Desmos in here. So now you should see Desmos. Does everybody see Desmos now? Yep, I hope you do. So here's another trick that you can do. This is a little harder to learn, but you can sum it up real fast. I can do sum, and as soon as I type sum, look what it does. Sums it up for me. And then I can go from 1 to, let's say, 7, because that's what I was doing before. And then what am I summing up? I'm summing up f of something over 2. So everything's over 2. So I'll put the 2 downstairs. Now what's upstairs? Or maybe we'll start it like this. We'll go, we'll start it at 3. Yeah, that's fine. We'll start it at 1. And then what's this guy? Well, this is 2n plus 1. Is that what we want? So do 1, we get 3. When we do 2, no, we don't get that. We have to be a little more careful how we do this. Bear with me 1 second. Here, we'll be more careful. We'll do 1 plus n times 1/2. So it takes a moment to figure this out, but if we multiply this by 2 now, this will give us all the middle terms, and then all we have to do is add the first one, and then the last one. And then if we enclose it all, I know I'm going fast, but maybe you'll take the time to check this out. And then we do it by 1/4, which is delta x over 2. You'll see we get the same answer. Now, why is this a little better to use this formula? Because you can modify this to do any number of trapezoids you want. Here I'm just doing 8, but I can easily do 100 with this method. So it's worth tinkering around with if you're brave, and you can, you know. And of course you can always check your answer. You can ask me. I'd be happy to talk about it with you guys. Questions, comments? And by the way, let me reiterate something. I can't emphasize this enough. There's no doubt that a few of you are looking at this gibberish that I'm typing into Desmos, and you're like, what in the world is he writing? Where is he getting it from? If you spend some time thinking about it, it's not that hard. The most important piece of advice I can give you is don't let the notation intimidate you. Once it intimidates you, it's like there's no hope. You got to say that I'm not going to let it intimidate me. So hopefully you'll say, I ain't going to let it intimidate me, and then you're going to go from there. And I can use the word ain't, because ain't a word. That's what they say. And by the way, this piece right here modifies. You can put, all you have to do is replace 1 with a, whatever your lower bound is, and replace this with whatever your upper bound is. And then this is just your delta x right here. And then this is delta x over 2. So perhaps it's something that you want to check out. I don't know. But I highly recommend that you do. Okay, does anybody have a question, comment? All right, so let's get back to the whiteboard. And so we've approximated the log of 5. And so we're excited. All right, so then the other problem that's very similar was problem 5, coincidentally, I guess. And so for 5, I don't want to steal all the fun for you, but I'll at least get you started because, again, it's very similar. So for 5, what you need to know is you need to remember that the integral from, say, 0 to 1 of 1 over 1 plus x squared dx is the arctan of 1 minus the arctan of 0. Now, how do I know that? That is the fundamental theorem of calculus. But the arctan of 1 is pi over 4. And if you don't know that, you could look it up, but you should know that. And the arctan of 0 is 0. So what's cool about this is what I have is the following. Pi over 4 is equal to this integral. And then what we can do is we can use numeric integration to approximate this integral, just like we did in the previous problem. And I asked you to use Simpson's rule, so this would be approximately 4 times its delta x over 3, and then it's f of x sub 0, whatever that is. Of course, you know that it's 0. And then what's the next one? Now remember, Simpson has this idea where it alternates. It's 4 f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3 plus 2 times f of x sub 4. And then there's 2 more. I'm really out of space. That was terrible planning by me. Here, let's go. Let's erase this and let's go do it on the next page. So we have all the room that we need. So we have the pi is approximately now. It's 4 times delta x over 3. Then it's f of x sub 0 plus 4 f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3 plus 2 times f of x sub 4 plus 4 times f of x sub 5. And then the last one is just f of x sub 6. That is what Simpson's rule says. Now, I don't expect at this point in your lives you have it memorized the way I do, but I use it all the time, and I teach it often. So that's why I know it. But you could figure it out quickly. And then what are your things? Well, what's delta x? Delta x is what? It's 1/6 because we're using 6 rectangles and our length of our interval 0 to 1. What is x sub k? Well, we know what x sub 0 is. It's 0. And then x sub 1, you can easily figure out is 1/6. And then x sub 2 is 2/6. X sub 3, 3/6. X sub 4, 4/6. X sub 5, 5/6. And then x sub 6 is 6 over 6, but we know that's 1. And then, of course, what is your function you need to use? It's this. That's what we're integrating. So now your job is just to calculate that number, and then you'll get an approximation of pi, hopefully. Does anybody have a question about this? So here's a good thing to think about. If I would have asked you before today, can you tell me a definition of pi that gives you any idea of how to tell me its value? Could you have done that? I mean, think about that. You've used and heard of pi your whole life, and the only thing you know about pi is that it's 3.14 because your teachers told you that, but you've never had a way of actually computing it yourself. And this is one of the first ways that you've learned where you can compute pi to any degree of accuracy you want. So if you wanted to, you can actually use this as a definition of pi. If you wanted to, you can define pi as this integral times 4. This could be your definition of pi. It doesn't clearly, with this definition though, it doesn't really make you think about a circle, but that could be the definition of pi. How we doing there? Everybody all right? Anybody have a question about this? This is fun math. We have participation today too, which is nice. I like some participation, even if it's faux, where you guys just type yes and yep. Thomas sees the whiteboard. He must be dreaming of mathematics. All right. Very good. By the way, approximation, and that's what we're doing here, is a very important theme in math and science. You don't really get a taste of how important it is and how complex it can be at this level. But you know, one of the things that we find out very soon in our journey to advanced math, particularly when it's applied to sciences, is that many things are impossible to compute. Be it a number like this, be it a function. So what we end up doing is we often have to use methods of approximating things. And these things, like I said, can be numbers that we're approximating. They can be very complicated mathematical structures like integrals, or they can be unknown functions. And we're going to give a little glimpse of that more before the end of the semester. But a good way for you to sort of understand like the importance of math in the role of science, not that that's the only importance of math. Some people love math because of its beauty and but what I guess I'm referring to is the applied applications of mathematics. Is approximation is a very useful tool. So if you read the book on the numeric integration chapter, what you'll see is at the end, they make a comment on the analysis of error. Like, how do we know how accurate it is? So here's a good question. I could say to you, what should n be so that my approximation is, accurate to 10 decimal places. So it turns out you can quantify all that. It's just too advanced for a class like this. And in fact, it's so advanced that error analysis is really its own subject. It's a branch of what we call numerical analysis, analyzing error. So these are questions you might want to ponder, you might want to investigate. It's cool how you learn these things. All right, does anybody have a question? Comment? All right, does anybody else have a question about this homework? Particularly, how about number 8? Did anybody get anywhere?
I was going to ask about number 8.
Yeah, so notice that I stated this problem different. I didn't throw this one in there with the other ones. And the reason for that is number 8 it's an important integral. the irony is this integral affects your lives in so many ways and you don't even realize it. Does anybody remember what the bell curve is, or has anybody ever heard of what's called the bell-shaped curve? I'm sure you've heard about that. Maybe your teacher said they're going to curve.
Yeah, it's related to the Gaussian distribution.
That's exactly right. So that's the fancy word for it, is it's the normal distribution or the Gaussian. And maybe if you had a prob and stats course, even if it's an elementary one, you would have talked about this integral. Excuse me, no, you wouldn't. They would have shown you a picture of the normal distribution, right? Which is a bell curve. So let's look at 8. So the function f of x equals e to the negative x squared is extremely important. And as you hit it on the head, you said it's related to the Gaussian distribution. It's related to, let's just say, it's important in life. I mean, it's everywhere. It's in economics. It's in finance. It's in biology. It's in, you know, engineering. It's in the study of how heat behaves, the study of waves. I mean, this function is everywhere. Its graph looks like this. It's a bell curve. And what's fascinating, if you go to Wolfram and you ask it the value of this integral, believe it or not, pi shows up. And you're like, holy, how in the world? So let me just explain to you what I mean by that. Hold on, I gotta go find it. I lost my page. So if we go to Wolfram, and if I just say integrate e to the negative x squared from 0 to infinity, you'll notice that it's root pi over 2. That's fascinating. And then it tells you this business of this air function, which I doubt many of you have seen or heard before. So it turns out that this is an extremely important integral. If you want, if I go to and Google Gaussian integral, you guys, I don't know if you're seeing this or not. Let's double check. Let's make sure you're seeing it. Yeah, there it is. So you'll notice that this is an, you know your Wikipedia page is spitting important stuff when you have all this. Okay, so if you want to read about it, great. So if I shade this right here, so the blue region has area equal to this integral. So it turns out not only does the integral converge, but it converges to the root of pi over 2. Now, you need Calc 3 to see why. However, that's not what I'm asking you to do. If you look at the homework, I'm not asking you to tell me what it is. I'm asking you to verify that it converges. And what it's going to illustrate is it's going to illustrate a very useful idea of using deductive reasoning. So we're going to be able to show that it converges, even though we can't tell you what the value is. So that's another important concept that we're going to encounter and then in the coming weeks is this idea of we might be able to, we might have a question like, what is the value of something? And we're not quite capable of answering that question exactly. However, we can get information that is at least useful to us. So we've sort of seen a little bit of this as far back as in Calc 1. If you remember in Calc 1, we studied this thing called the intermediate value theorem. And that was an example of what's called an existence theorem, in that the intermediate value theorem says, okay, if I'm looking for the solution to an equation, I might not be able to tell you exactly what it is right away, but I can tell you where it is located. What neighborhood does it live in? What values is it close to? And then using that information, I can deduce new information. And so this is a similar thing we want to do. And let me motivate it this way. So the best we can do with Calc 2 tools. So I'm not saying you're not smart enough to get it. I am saying that we haven't taught you the necessary, or excuse me, the tools you need to show what the integral is exactly. So the best thing we can do with Calc 2 tools is, one, verify it converges, and two, approximate its value. That's all we can do with Calc 2 tools. And by the way, I should finish my thought before. When I said this affects your life in every way, it really does. I mean, insurance companies use statistics and probability to determine what kind of premiums you're going to have, what kind of rates. When you go to a bank and apply for a loan, they're going to say, okay, where do you fall at with your credit ranking? What age? They're going to use these sort of ideas from probability and statistics to determine not only if they're going to give you a loan, but how much and what kind of interest rate are you going to get. There are all kinds of ways that these things affect your lives, I should say. Cool. So what we'd like to do is study it. So there's a few ways you can study this, and what we're going to do is I'm going to show you my sort of logic. So the first thing you might ask is, dyslexia lately? So a question that is always asked by students is, why can't we just use the FTC? Well, friends, we don't know an antiderivative for e to the negative x squared. So basically what I'm telling you is that you can spend the rest of your life looking for a function whose derivative is this, that is a elementary function, one that you would understand, and you're never going to find it because it doesn't exist. Let me repeat that. There is no function out there that can be written as an algebraic expression in sines and cosines and all that crap. There's nothing that will look like a function to you whose derivative is e to the negative x squared. So what that means is we can't just write the integral as the difference between the antiderivative at the top and bottom endpoints. We can't do that. So what do I mean by that when I say use the fundamental theorem of calculus? Well, again, let's just go to a simple example. If we want to integrate 0, 1 of x squared dx, that's simple. We just say, okay, that's 1/3 x cubed from 0 to 1. which of course you guys know reduces to 1/3. This works because we know the antiderivative of x squared. This same reasoning doesn't work with e to the negative x squared. So if we tried to integrate even 0 to 1 of e to the negative x squared dx, you can't plug anything in there because there's nothing there to plug into. So I hope that makes sense. There are lots of functions where the fundamental theorem of calculus doesn't apply. So if we can't do it between 0 and 1, how can we do it between 0 and anywhere? So we have to get creative. So here's what I'm going to do. I'm going to use my medulla oblongata, if you will, my brain. I think that makes sense. I don't know. Does it make sense? So what my brain is based off of is that I'm going to use information about known things to gather information about unknown things. I mean, that's a theme in science, right? That's a theme in math. So the key observation is to compare the function to a close relative of it. So perhaps the best way for me to get that going for you is to go to Desmos. So what I'm going to do is I'm going to graph two functions. I guess I should show it with you. I'm going to graph two functions. I'm going to graph y equals e to the negative x squared, which this is the guy we're after. And let's zoom in on what's happening here. As I told you, this is the bell-shaped curve. So let's zoom in over here because we're not interested in what's happening when x is negative. All we care about what's happening over here. And by the way, this has an asymptote at 0, and it gets there real quick. Right? I mean, down here, look at this. When you plug values bigger than like 2 into this function, they're really close to 0. It's very small. So we suspect that this integral converges. But we can't do it with our tools because we don't know how to integrate e to the negative x squared. We don't have an antiderivative. So then we ask ourselves, is there a function that we can integrate easily that's related or has similar behavior to this? And so the first thing I would encourage you to do is think about the following. If I look between 0 and 1, if I draw a square, I think I can draw one here. So if I draw this square, whoa, that's bad. Let me use my line here. I'll use this. If I draw this square, would you guys agree that the square is bigger than that purple region, right? I think everybody would be in agreement that, let me shade it in this way. If I shade this in, whoops, I wrote it wrong. Hold on, bear with me. So I think you would all agree with me that the red square is larger than that area that I have shaded in. So let me change the color to make it a little more appealing. The blue. So again, the red rectangle has area 1. That blue shaded region's got to be less than 1, right? We all agree that that has to be less than 1. Now, we can't tell you exactly what it is, but it's got to be less than 1. Okay, so the idea is, can I do something similar? Can I get information about the other parts of the area under the curve? So what I'm going to do is I'm now going to look at a very similar function. I'm going to look at y equals e to the negative x. And I don't care about it other than when x is greater than 1. So I'm going to change the color here so we get we get some information here. Make this green. So I hope what you guys understand from this picture is 2 things. And don't think calculus right now. Just think what a 5th grader would say. 5th grader would say the blue region is inside the red square. 5th grader would also say the green line, the green curve, is above the purple curve. So what we can do is we can write these things down in terms of integrals, though. Instead of writing them in English, we can write them in terms of integrals. So let's do that. So what I'm going to do is I'm going to draw this picture again. Only I'm going to draw it here. We're going to sketch it. So here's my y-axis. My x-axis. So here's what I know. So let's take, what was it on? In Desmos, it was purple, so we'll use purple again. So if I'm up here at 1, the curve comes down like this. We have this asymptote, right? I hope this doesn't work. Oh my Lord. All right. Oh my God, undo it. Undo it, there you go. Okay, great. Now, we also had a square. So if I go here and draw a square, so let me, this is 1 on the x-axis. So if I take my red square, so remember this purple curve, this is y equals e to the negative x squared. Now, if I draw the green curve also has an asymptote, but it is above the purple guy. So the green curve is the graph of y equals e to the negative x. Coincidentally, if you finish this drawing, it actually, the green guy comes down like this. It's not, well, it's curved. So it actually comes down like this. And so if I take my blue like I did on the previous page and I sort of shade it in, so what's the blue region? Let's do our fifth grade minds again. So what's the blue area? The blue area equals the integral from 0 to 1 of e to the negative x squared dx. And that clearly has to be less than 1. Why does it have to be less than 1? Well, 1 is the area of the square. So that's our 5th grade reasoning here. Does anybody have a question about that? Okay, great. So from 0 to 1, we understand the size of this integral. So we know that it exists clearly. Now, the issue is going to be what happens from 1 to infinity. But from 1 to infinity, we got some information, and it's not hard to deduce this. And that is this integral, which is what we're after, 1 to infinity, of e to the negative x squared dx, this has to be less than the integral of the green curve, which is the integral from 1 to infinity of e to the negative x dx. I mean, again, think 5th grade mind. Look right above. What's going to be larger, the area under the green curve or the area under the purple curve? So if we write that in terms of calculus notation, in terms of integrals, we have that integral relationship. Does anybody have a comment or question? Now here's the beauty. We know how to compute this guy. This green one, we did. I believe we actually did it on Tuesday, if I'm not mistaken. Even if we didn't, I think maybe we did a slightly different one. Maybe we did e to like the -5 or something. But on the homework, we asked you to do e to the -3. Either way, the method is the same. If you compute this integral, you arrive at a very simple number. This is actually equal to 1 over e. Okay, so if we're telling you one integral must be less than another one, and that other one is a finite number, in particular 1 over e, then we can clearly see that the integral we're interested in has no other choice but to converge. So let's put all this together. We have to put the pieces to this puzzle together. Let's summarize it. So what we've done is we've deduced that this integral indeed converges. And we even have a crude estimate. So what's our crude estimate? Well, we know that it has to be positive. And we saw that we can break it into 2 integrals. We can break it up between 0 and 1. And then 1 to infinity. And from the previous page, we know this piece is less than 1, and we know this piece is less than 1 over e. So what we get is the integral from 0 to infinity of e to the negative x squared dx is approximately 1 plus 1 over e. Now, notice I said crude. This is not a good approximation, because if you go back to our picture, we left a lot on the table. We have this big error over here. We left a ton on the table here, and we even left some on the table here. So this is not a good approximation, but it's a crude one. And you can use similar ideas to get better. Does anybody have a question?
How much do you just infer from the graph of a function whether or not that function converges? Like,
What do you mean? I'm not, you can't do that. You can't look at the graph and guarantee if it does.
Okay, that's just what I was wondering.
Yeah, no, that's illegal, but I'm not doing that. I'm using the graph to get some intuition and some sort of investigative reasoning, but I am not looking at the graph to determine this.
Right. I was just wondering.
Yeah, so if you want, maybe I should have been more clear. Note, we have a fact. If this is a basic property of integrals, if f is less than g on an interval, then the integral of f must be less than the integral of g. So that's the reasoning I'm using here. Now, the graph is not good enough evidence, but if you do some algebra, you'll clearly see that e to the negative x squared is less than e to the negative x. You could just, you can use different types of reasoning to show that. But that's a good point. So that's a subtle point too. I'm not just looking at the graph. The graph could be misleading. Now, what I'm doing is I'm using reasoning that is sort of verified by looking at the picture. So it's actually a good question, Paul, because the reasoning I'm using, how do I know? Look, just because the graph shows the red rectangle or red square being bigger than the purple thing, but don't forget, how do I know that for a fact, not just looking at the graph? Well, look at e to the negative x squared. Think about it. That's the same as 1 over e to the x squared. That's always less than 1, always. I mean, 1 divided by something bigger than it is always, always, always less than 1. So just by that reasoning, that's what gives me this picture. So another way of saying this is I could have used the information that I know about these functions to sketch this graph. Does that make sense? Now, another thing for me to be completely fair with you, I would never expect you to figure this out on your own. Now, if you read the book, you'll see a similar argument. If you look it up on the internet, you might find it. But without me showing you this argument, it's highly unlikely that you would come up with this line of reasoning on your own, not in an ordinary amount of time. Now, maybe if you said I'm going to lock myself in a room until I get it done, you might figure it out after a few weeks. But you're highly unlikely to get this on your own until someone shows you it. But this is a glimpse into one of the things that mathematicians do, is they get information about one unknown thing by comparing it to a known thing. And by the way, I shouldn't be so, maybe I should spell this out for you more. This right here, you should verify this. Now, if you've done problem 7b on your homework, it's almost identical to that. It's not the same, but it's almost identical. So your question is a good one. You got to be very careful with, I didn't just make this up. This is a common theme. This type of using deductive reasoning is very common in mathematics. And that's one of the things we want to try to enlighten you on in this course. It's not just always plug and chug. Now, of course, you're going to get demoralized because you're going to say, I would have never thought of this. And most of you are probably staring at this like, what the hell is he even talking about? And I empathize with that because when I first saw this, I was like, what the hell are they talking about? Right? So I get your pain. It is a struggle to learn this. I'm not going to pretend. But a problem like 8 is a much more higher level of reasoning than the previous ones. So, you know, when you get discouraged because you might not make sense of it, you can remind yourself that, yo, this is hard. And that's okay. And by the way, sometimes you're like, oh, what do I write for the homework or something? Well, again, the homework is there for practice. You turn the homework in, unless it's completely terrible, you're going to get a good grade. I want you to try to learn this stuff. And that's why I phrased the questions I did the way I phrased it that way. Is he correct? I mean, I'm not telling you what to do. I was, you know, in an ideal world as an educator, as someone who loves to learn, I hope that you guys would spend some time thinking about what can I do? You know, that's why I worded the question the way that I did. So that maybe you try a couple weird things and you get nowhere. But then if you put some time into this and got nowhere and then you saw this argument, then there's a learning experience to be had. Anyhow, that's my philosophy, at least. I don't know if you buy it. But. Does anybody have a question, comment? Does that make sense, Paul? I don't know.
Yep.
Yeah. You know, because really, if you look at some of these problems, and by the way, you know, if you look at problem 4 in the homework, you could do the same thing with e to the negative x squared, and then you could get a better estimate. You know, you could use a Simpson's rule or a trapezoid rule to estimate the integral from 0 to 1, and then you get even a better estimate. Maybe I'll ask you to do that on the test. That'll be a good test problem. We'll work it. We'll ask you to do a bunch of things, and then you'll be, oh my God, aha. All right. Any comments, questions? It's probably a good place for us to stop because we're already an hour and almost 40 minutes in. Your attention spans, if you're still with us, are probably dwindling. So I would highly encourage you start thinking about this stuff and then doing these homework problems so we're ready for the test next week. Comments, questions, concerns? All right, well then if that's it, I say have a great weekend. Thank you for joining. I hope that you spend some time asking questions to yourself, and if you want, emailing me. You can blow up all my emails saying, where's our grades, O'Grady? You can have a mutiny, whatever it is. I will do my best to get them up for you. If you have any questions about the test or whatever, please reach out. Otherwise, have a great day. All right, guys, thank you very much. Take care.